Hi everyone, I'm Marian Zaki and I'll be presenting our paper Effective Access Control in Shared Operator Multi-Tenant Data Stream Management Systems. This work has been completed at the University of Pittsburgh Computer Science Department by myself along with Adam Lee and Panos Chrysanthis. So let's get started. So what is the whole idea of multi-tenant data stream management systems? Basically, we have a bunch of data providers or data applications that are sending data in the form of high velocity data streams, and examples of those data applications can be sensor-based monitoring applications, financial applications, healthcare applications, social media, etc. And on the other side, we have data consumers who are interested in querying those data streams and extracting useful information out of them. And in the middle lies the data stream management system, which is capable of handling those incoming data streams and processing queries in real time to provide answers to the queries submitted by data consumers. So how exactly does the data stream management system handle this high velocity incoming data streams and queries of users? Let's take a look at this. Over here in this diagram, we can see that the users, streaming applications, they can register continuous queries in the system. And the data stream management system runs local query optimizers. And what the query optimizers does is it looks at those continuous queries and identifies those who are querying the same data streams and those queries that have common sub-expressions in them. And from those queries, it can build a shared operator network in which one or more queries can be actually sharing one or more of those physical operators. This is a very simple explanation of how data stream management systems handles continuous queries. Another part of the system is the access control. In data stream management systems that host sensitive data, for example, patient monitoring data or financial and banking data, data providers are interested in restricting the data access via access control policies. And those policies, basically what they do is they describe the conditions under which users are permitted to access specific data streams. Accordingly, we can see that the data users may be granted or denied access to certain queries as they are executing. The question that arises is, how can we enforce access control in a scenario where we have a shared operator network that is shared by multiple users? What happens if access control policies change while this network is executing? What happens if users' credentials change while this network is executing? And these questions provided this particular research that I'm presenting today. In our research, we looked at this interesting problem. And so for today, I'm going to start by providing a motivating example to better understand the problem, and then I'll move into describing our system model and assumptions. I will present our contributions, and we presented our solution as a set of, introducing a new set of operators that we refer to as privacy switches. And we designed an algorithm to strategically place those switches in the network to allow for access control to take effect while the network is executing. Then I will present our simulations and our results from our experimentations, and finally I will conclude. So let's take a look at one motivating example, and I've chosen to present you with the smart healthcare industry example because in the recent years it has gained a lot of interest from developers and researchers to look at the implications of smart healthcare industry. And if we look at this industry, we see that there are now in the market a lot of wearable smart devices that are equipped with various biosensors that are used to measure and monitor diverse health data of individuals. For example, the blood glucose levels, blood pressure, oxygen saturation, heart rate, and many others. Recently, I read that Apple Watches are looking into providing biosensors in their Apple Watch to monitor COVID-19 exposure. And very interesting applications can be implemented using the wearable smart devices. On the other side, hand side, it goes that without saying that this information that are provided by those smart devices are critical information and of a highly sensitive nature. And most of them fall under the HIPAA rules of protecting individuals' health information. And from there, we need to consider access control, who can view this information, who can run queries on those data streams that are generated. Here we're looking at two different queries that are running using some smart devices to collect some bioinformation. But what happens is those queries are running over the same set of data streams, stream 1, stream 2, and stream 3. And if we analyze the queries, we see that they have some common sub-expressions. And accordingly, we were able to build this shared operator network to execute both queries simultaneously. Now let's take a look at a simple access control example. Let's assume that Alice, Bob, and Jack, all three of them, are allowed access to all three data streams, and accordingly they can run queries over those data streams. And so the network is executing, there's no problem, all three users are accessing the query results. What happens if the access control policies change and Alice and Bob are denied access to query 1? How can we enforce those access control without disrupting the operation of the shared operator network? Because there are still other users. In this example, Jack is still allowed access to the output of query 2. In the past, there has been some solutions that are proposed, but we consider those solutions as naive solutions. One of those solutions is pre-filtering and post-filtering. And pre-filtering means cutting off the streams that are feeding into the network. And obviously, this solution doesn't work in the case of multi-tenant operator networks, because then you're cutting off the stream to all the other parts of the network that are still allowed, where some users are still allowed access to those. On the other hand side, the post-filtering means cutting off the query outputs to those users who are denied access. And we can see that this is just a waste of resources, because all what it is doing is we're allowing all the operators to execute, and at the very end we're denying the output, and it's a very wasteful solution. Another also naive solution is to halt the shared operator network from executing when access policies change, and execute each query independently. And whenever the access is granted back, then we can divert back to the shared operator network. It is obvious that this solution is very inefficient, because what we're doing is we are constantly constructing operators networks, different versions probably of interleaved queries. And we're diverting the input streams to execute on those different versions. This is a very tedious solution, and in the worst case, we can be looking at an exponentially large number of networks that we have to keep track of and maintain in the system. From here, we started thinking about this problem, and we thought, is there an efficient solution to allow access control over interleaved multi-tenant operator networks that doesn't require us swapping execution between different networks as changes take place to access control? And our solution is actually a very simple solution that can dynamically reconfigure the shared operator network as changes to access permission takes place. And in our solution, we presented a new set of operators that we refer to as the privacy switches that we embed in the network and strategic locations inside the network. And those switches are capable of turning on and off to allow or disallow the data streams from flowing into certain operators or even branches of operators. And so they allow for partial data flow through the network while maximizing operators sharing, and that's a very efficient way of running operator networks. They also eliminate the need of migrating streams between different copies of operator networks. So let's start looking at more technical details of our solution. In our paper, we defined the operator networks as directed acyclic graphs, and each network is defined by a set of vertices, edges, and labels. And the vertices represent the different queries, the query operators. The edges allow the operator, the output of one operator to flow into another operator. And finally, the labels on the edges define the formal language of a query in the form of an operator and predicate. As for our access control model, we assume that the data stream management system can enforce query-based access restrictions that can be specified by either the data stream providers or the data stream management system. Our authorization policies operate on the set of continuous queries and users or user rules and attributes. And our model is very generic that it can accommodate any access control model, whether it's an RBAC, ABAC, or DAC models. That really doesn't make a difference in our model. It's very generic in that essence. And then we do have a mapping function that can take a set of continuous queries and identifies the data streams that are involved in executing those queries. And accordingly, the data stream management system can construct for every proof of authorization what we refer to as security punctuations. And we'll talk in a little bit more deeply about what security punctuations are. And the data stream management system will inject those security punctuations in the corresponding streams. So what are security punctuations? We've adopted the notion of security punctuations from the work done by Rima Nahmi and her colleagues. And security punctuations are considered metadata in the form of predicates that are inserted or injected into the data streams. If we look at the structure of one security punctuation, we see that it specifies the query. The data description part is the stream, in our case, the data stream. And then in the security restriction part, it specifies what type of access control model that is used in the user IDs. And then in the sign part, this is a positive or negative. And basically what it is saying here is that this particular user or group of users are allowed or denied access to that particular stream that is feeding into a particular query. And then finally, of course, every security punctuation has a timestamp to identify when was it created by the data stream management system and injected into the data stream. In our solution, we presented three different types of privacy switches. The first type is what we refer to as initial privacy switches, and those are placed at the input streams at the beginning of the operator networks, and they're capable of shutting off streams from flowing through the shared operator networks. And this happens when there is a total loss of access to the query results as the access control permissions changes. The in-network PrSs are embedded within the operator's network, and they shut off the execution of certain operators within the network. And then finally, the terminal privacy switches are placed at the query outputs, and they perform the operation of post-filtering. They act more as a multiplexers that can branch out the query output to multiple users. So our placement algorithm defines how all three kinds of privacy switches are inserted in a shared operator network. And the algorithm is very generic, but here to the right we're looking at, again, the same motivating example that we've looked at earlier. The algorithm takes as input a shared operator network defined as a directed acyclic graph, and then it starts by iterating over the network starting from the query outputs. It inserts the terminal switches, and then it backtracks and traces the network backwards until it identifies what we refer to as common prefix operators, and those are the operators that are shared across multiple queries. We assume that the data stream management system, specifically the query optimizer, will be able to identify and annotate those operators as common operators during the process of building the network from the beginning. And so the in-network privacy switches are inserted right after the branching out from the common prefixes. And then finally, for every input stream, we insert the initial privacy switch. Next, let's take a look at the execution of the privacy switches and how they enforce access control and dynamically configure the shared operator network. Again, to the left, we see the generic algorithm. And to the right here, we're looking again at our, without loss of generality, we're looking at a particular example just to demonstrate how the network behaves as access control changes. And so here we have Alice, Bob, and Jack, all three of them are allowed access at the beginning of the network to both queries. Every in-network privacy switch has a counter that we refer to as access counter, and that counter identifies how many users are accessing that particular query output. And so initially, all counters are set to 2. Once the privacy switches encounter in the input stream a security punctuation, they start analyzing the data and the security punctuation, and they behave accordingly. And so in this example, the security punctuation arrives saying that Bob is now denied access to query 1. And so all the privacy switches that are in the path of executing query 1 are going to accordingly decrement their counter by 1. And the terminal switch that keeps track of how many users are accessing the output will deny access to Bob, and only Alice will continue to receive the output of query 1. If later on it happens that Alice is denied as well access to query 1, then again the counters are going to decrement, and if they reach 0, that means that there is a total loss in this branch, and the switches are going to turn off here, reserving the execution of these 2 operators. And if later on any of these users gain access back again, the counters are going to increment by 1, and the flow of the data streams are going to continue moving here. And so as you can see, it's a dynamically configurable network based on the access control policies that are being demonstrated in the data streams using the security punctuations. To test our performance in our system, we have implemented a random generator that generates directed acyclic graphs that resembles shared operator networks. And this tool that we've implemented, it takes as input the number of input streams, the number of interleaved queries, how many users are executing those queries, then a required number of query operators, and the degree of sharing, which is the number of operators or the percentage of operators that are defined as common prefix, and accordingly it generates directed acyclic graphs resembling shared operator networks. Of course, we have to enforce a lot of rules in the tool to ensure that the random graphs that are generated are actually equivalent to shared operator networks. So our first set of experiments, we varied the degree of sharing, and then we compared three kinds of networks. So one network that has absolutely no sharing, each query is running as a separate operator network, and then shared operator network without the privacy switches, and then shared operator networks with privacy switches embedded. And we varied the degree of sharing across by running the networks multiple times. We have two different setups of networks here. One that consists of 15 operators and 3 interleaved queries, and then the one to the right has 25 operators and 5 interleaved queries. The interesting observations from these simulation results is that the average execution time savings between the non-sharing and the shared operator networks was approximately 95%, and this shows the benefits of running shared operator networks versus running each network independently. The second observation is that PrSs added negligible overhead to the network, and the reason to this is that the execution of PrSs is presumably cheaper than query operators because they only execute infrequently, only once when they encounter a new set of security punctuations in the strings. We've also noticed that execution time is really insensitive to the degree of sharing. The other set of experimentations that we ran, we wanted to test the performance of the network as access control permissions start varying. And so we looked at the different combinations of access loss in a network that is interleaving 3 input streams. And we've noticed some really interesting observations by running those simulations. We've seen that our technique proved to perform better in the case of total access loss with queries that have less common sub-expressions in them. This shows greater benefits of our multi-tenant shared operator networks, even if there are lower degrees, even if there isn't high sharing across the continuous queries. And that was a really interesting observation that we came up with. Also in our appendix, and I'll leave that to the readers to read, the detailed formal proof of the correctness of our operation of our privacy switches. So finally, to conclude this presentation, we're capable in this work to configure interleaved operator networks in a dynamic way by using the privacy switches to allow or deny access to certain query results, complying with the access control policies defined by the system. And as those access control policies change, there is no need to demolish and rebuild networks. It's the same network, it's just being configured differently as access control changes, or even users' credential changes. The implications of this is we are able to build a dynamically configurable multi-tenant network that potentially can save time, bandwidth consumption, and several monetary costs associated with configuring and executing shared operator networks on clouds, which is very interesting results that we came up with. Well, thank you for listening to my presentation, and I'm providing our contact information. If you have any questions, please feel free to email us at any time. And thank you one more time.